Welcome, ladies and gentlemen. Let's go ahead and take a look at our Bellwork today. We can easily tell the difference between indefinite integrals versus definite integrals because of the limits on our integrand symbol. So in our first one, number one an indefinite integral or a definite integral? Grace? An indefinite integral, absolutely, where the answer to an indefinite integral evaluation is a function, right? A function in its own right with its own domain and range. And so we want to make sure that we're finding an antiderivative function for my integrand such that when differentiated produces that original integrand, right? Some key things to note when evaluating an indefinite integral, we have to include that plus c, that constant of integration. So if we can differentiate functions term by term when they're connected by a sum or difference, so too can we integrate term by term. So we can go ahead and just break this up and perform several antidifferentiations. So for our first squiggle underlined green, I'm thinking overall power rule, where I know that my constant multiplier is going to stick around for the party. So I'll leave that 6, and I'll focus in on my x to the 1/2. Remember, a radical x, square root of x, is x to the 1/2. So when I apply my power rule, I'll add 1 to the current exponent. 1/2 plus 1 is 3/2, and then divide by the new exponent. Well, keep in mind, dividing by a fraction, 3/2 is the same as multiplying by the reciprocal 2/3. So there's an antiderivative function, right, for the squiggle underlined green. We'll go ahead and now focus to our double underlined blue function, -1 over x squared, and again we'll use power rule, right? Power rule, where my current exponent is -2. And so I'll go ahead and keep that constant multiplier, -1 times, and now I'll apply the power rule. Current exponent, x to the -1 plus 1, x to the -2 plus 1 would become -1. So I get x to the -1, and then divide by the new exponent. So -1 is the new exponent, so I'll divide by -1. There's an antiderivative function for my underlined blue. And then lastly, we can apply the power rule to 10 over x, the way we applied the power rule to 1 over x squared. Why can't we just use the power rule to find an antiderivative for 10 over x? Right? Why can't we just use the power rule for that? Megan?
Because you can't have x to the 0 as...
But yeah, when we add 1 to our current exponent, -1, we get x to the 0, right? And it's okay to have x to the 0, right? That would just be the 1, except when we divide by the new exponent, right? When we divide by the new exponent, then we'd be trying to divide by 0, and that's undefined. So we can't apply the power rule. But we already know an antiderivative function for 1 over x. If I keep my constant multiplier here, 10, what's an antiderivative for 1 over x? What's an antiderivative for 1 over x? Katie? Absolutely. The only thing we need to make sure when finding an antiderivative using a natural log is to include absolute value bars around my input. That will preserve the domain of my original function. So while 10 over x is defined for both negative and positive values, the regular natural log of x only exists for positive inputs. So to remedy that and make the domains match up, because again we're finding an antiderivative function with the domain and range, we need to include absolute value bars on our input x. And then don't forget the plus c. All right, so let's go ahead and do one step of simplification and see how it looks. So we've got 6 times 2/3 is 2 times 2 is, I'm getting 4x to the 3/2. Negative divided by a negative is a positive. 1 over x to the first plus 10 natural log of absolute value of x close bars, and then plus c. Well, go ahead and take a look at your antiderivative function and raise your hand if you had the same. So who had the same? Yes, that's great. So that's like 3 antiderivative problems for the price of 1. Nice job. Let's go ahead and take a look at the number 2. Go ahead and tell the class when I call your name. Is number 2 an indefinite integral or a definite integral? Blake? Definite. A definite integral, absolutely. It's easy to recognize because we have limits on our integral symbol. A definite integral, right, isn't a function, an antiderivative function with a domain and a range. A definite integral is a numerical quantity. Right? Geometrically, bless you. Geometrically, it represents the area between the integrand function and the x-axis. It could also represent in context a product of the dependent variable units and the independent variable units on the integrand's graph. And so this is a number. At the end, we should get something like 50 or -17/3, right? So a definite integral is a numerical quantity. Let's go ahead and see what we get for this definite integral when we evaluate it algebraically and exactly in accordance with the fundamental theorem of calculus. That was last class, so this is a big deal. The mean value theorem provided the bridge right? The missing link that connects indefinite integrals with definite integrals and will allow me now to find this exactly and algebraically, right, without the use of a calculator, and then I can check with my tech tip, right, my math 9. So here we go. I need an antiderivative function for secant squared of x. Go ahead and tell the class an antiderivative function for secant squared of x when I call it. All right, what's an antiderivative function for secant squared of x? Sydney?
I said tangent.
Tangent of x, raise your hand if you had tangent of x for your antiderivative function. Good job. And so we'll go ahead and say tangent of x. And if we were doing an indefinite integral, we know we'd include a plus c. But because we're evaluating a definite integral, right, and the result will be numerical quantity, whatever constant plus c might have been attached to this antiderivative function will disappear when I do the subtraction of my antiderivative function and evaluate at the lower limit. So I don't need to include a plus c if I have limits on my integral symbol, but I will include my notation here from lower limit pi over 6 to upper limit pi over 3. And so when we are evaluating a definite integral, we don't have to include the plus c in our antiderivative function. It would technically be there for an antiderivative function, but I know it's going to disappear when we do our evaluation. All right, let's go ahead and go gadget arm and evaluate my antiderivative function at the upper limit. So the tangent of pi over 3, and then minus the antiderivative function evaluated at the lower limit, minus the tangent of pi over 6. So we'll go to our unit circle, right? And we know that the tangent of pi over 3, right? The tangent of pi over 3 is equivalent to the sine of pi over 3 over the cosine of pi over 3. So sine of pi over 3 is root 3 over 2. Over cosine of pi over 3 is 1/2. So root 3 over 2 over 1 over 2 is just root 3. So I get root 3 for my first evaluation. Minus, and then the tangent of pi over 6, that's the sine of pi over 6 over the cosine of pi over 6. So at pi over 6, the sine is 1/2. Over the cosine of pi over 6 is root 3 over 2. So 1/2 over root 3 over 2 is 1 over root 3, or root 3 over 3. So I'm getting exactly root 3 minus root 3 over 3. So root 3 take away a third of root 3 would be 2 thirds of root 3. So I'm getting 2 root 3 over 3. Wow, well, that's suspect. So I want to go ahead and check that, right? I want to go ahead and check that using my check tip. And so once again, without doing a graph and messing with my window, I can do math 9, right? I can do that second method, math 9, in order to get a numerical approximation for the value of a definite integral. My lower limit here was pi over 6, so we'll do pi over 6. My upper limit was pi over 3. My expression was secant squared of x. So how am I going to enter that? Very carefully, I'm going to do 1 over cosine of x. Right, so I'm going to do 1 over cosine of x, quantity squared to get my secant squared of x, and we'll simply integrate that with respect to x. Take a minute and make sure you're comfortable with your math type or your classic. If you're doing classic, you'll just do math 9, it'll say fint, you'll do expression, secant squared x, comma, with respect to x, comma, lower limit, comma, upper limit, right paren, enter. In either case, we should get a decimal approximation, and I wanted to see if my 2 root 3 over 3, I wanted to see if my 2 root 3 over 3 was equivalent to that decimal, and how do we do? Yes, math works. So exactly and algebraically, we found the value of that definite integral, and we verified it using our tech tip. We got it the same decimal approximation when we use math 9. What questions do you guys have about number 2? Okay, 1 to go. Let's take a look at number 3 then. Oh, goodness gracious. So this integrand is much more complicated than the previous, right? This is the first case where I'm going to have 2 separate parts of my integrand function. So the key here is determining how those 2 parts relate, right? We need to determine which part is the derivative of the other part or a portion thereof, in accordance with the chain rule, right? In accordance with the chain rule, we need to figure out what's the overall function and what's the inner function. So what I want you to do is go ahead and see, is the overall function here a sine function, a cosine function, or a power function? Right? What overall antiderivative rule are we working towards in number 3? Are we thinking this overall a sine function, overall a cosine function, or overall a power function? What antiderivative rule are we working towards here? What do you guys think? Benton and Michael? Power, overall this is a power rule, right? It's a power rule where my base just isn't x to the 7th. My base isn't just x, it's cosine of 4 theta plus 5. So my overall rule here we're working towards is a power rule. So if we were to choose u to be the base in this power, right, then when differentiated, the derivative of the base would help kick out some of that sine of 4 theta there. And that's the relationship between the two pieces. That sine of 4 theta is acting as a portion of the derivative of the base in this power function. So let's go ahead and choose u to be cosine of 4 theta plus 5. Right? So we're working towards an antiderivative for u to the 7th. Right? We know that if we were to replace the cosine of 4 theta plus 5 with u, we get u to the 7th. And now we just need to see how this sine of 4 theta, d theta, relates to u so that I can complete my substitution, integrate with respect to u since I now have u's in my integrand function. So let's go ahead and take du d theta. So du d theta, the derivative of both sides with respect to theta, would be derivative of cosine of 4 theta would be opposite of sine of 4 theta times the derivative of the angle would be 4, and so it looks like I get, after multiplying the d theta over, I get negative 4 sine 4 theta d theta is equal to du. And what portion did I need to complete my substitution? I needed the red squiggle underlined sine 4 theta d theta. So I'm going to go ahead and solve for the red squiggle underlined sine 4 theta d theta and see what will complete my substitution. So what do I need to do? It looks like the relationship between sine 4 theta d theta is negative 1/4 du. Right? Everybody see that? Negative 1/4 du must be equivalent to the missing pieces sine 4 theta d theta. So I can now complete my substitution. I'll go ahead and put in negative 1/4 du to replace, right, my sine of 4 theta d theta because that's what it's equivalent to. Now I can integrate with respect to u. I need to have that du there so that I can integrate with respect to u in my antiderivative function, and then rewrite finally with thetas at the end of the thing. So let's complete our antidifferentiation. I'll grab onto that constant multiplier, negative 1/4, and I'll kick it out front, right, so I don't trip on it. So there's my negative 1/4. Now I'll focus in on my u to the 7th power function. I'll apply the power rule in reverse. I'll add 1 to my exponent. 7 plus 1 is 8, divided by my new exponent. So that's divided by 8. And we'll need a plus c. All right. So it looks to me like we get negative 1/4 times 1/8 is negative 1/32. Could it be u to the 8th power? But u was cosine of 4 theta plus 5. And then plus c. Go Gardner. So I get negative 1/32 cosine of 4 theta plus 5 to the 8th plus c. Raise your hand if you had that. Did anybody get all the way to the end? Great. How can we check and see if that's right? Well, we can always differentiate. So I could always check and see if my antiderivative function is correct by differentiating. We'll just do a quick derivation to make sure we're good to go. So constant multiplier, negative 1/32 times power rule, where my overall function is a power function, exponent times the base raised to 1 less times the derivative of the base. It's just that my base is an x. It's cosine of 4 theta plus 5. So the derivative of my base is opposite of sine of 4 theta times 4. Let's check it. See? The 4 times the 8 is 32. Divided by 32 is going to cancel those out. Negative times the negative is a positive. It looks to me like I get my sine of 4 theta right there, and then I get cosine of 4 theta plus 5 to the 7th, matching my original integrand. Awesome. What questions do you guys have on number 3? Okay, so today I'm putting in, your textbook doesn't formally address u substitution at all. So I was just sharing it with you as a technique that will sometimes help you because it can algebraically be used to generate that missing constant, in this case negative 1/4, right, using a systematic procedure. You don't have to use u substitution on the Unit 5 test if you know your derivative rules very well. And to ensure that, right, to help ensure that, I should say, again, we're having that rules quiz the last 20 minutes of class today. You have to know your derivative rules very well. We will need u substitution for 2 things during second semester, and so it's good to introduce it now. I'm putting in Copywork today that is a little math notes printout with an example and a rationalization for U substitution and why it's an appropriate technique. And so we should be getting that back next time from Copy Center, and I'll share that with you as a supplement because there was nothing in your textbook, and I wanted to have you give you a hard copy, something with with kind of some U substitution notes. All right, let's go ahead and take care of our hotel number 7 at this time. Please make sure that your name first and last, number 7. Clear the label, give yourself credit for those you complete out of 24, please. Divide, enter. Multiply by 2, and then box that in the table. Score nice and big rounds to the nearest half point 0 to 2. You don't need to include your half sheet because there's no picture, but I would ask that you staple multiple pages together. I'll close the blinds so that we're not blinded by the light. Please pass them in, ladies and gentlemen. Front rowers, make sure they're facing the same direction. I appreciate your help. And we can get going with our festivities for the day. Everybody good with number 7? Number 7? Okay, ladies and gentlemen. At this time, I ask that you go ahead and direct your attention to your note sheet for day 7. Our definition of a definite integral, right, relied on a limit of Riemann sums, where we use Riemann sums to approximate the area underneath the function f, right, in between the function f and the x-axis over some interval a to b. And so we started off with the area of a typical rectangle whose height times width gave me the area of that single typical rectangle. So we had f of c sub k times delta x sub k, and this represented the area of a typical rectangle. Well, then we summed up the areas of all my rectangles from 1 to n rectangles, right? And that gave me an approximation for the area underneath the curve. To make that approximation equal to the definite integral, that integral from a to b of f of x dx, to make it the exact area underneath the curve, we needed to let the limit of those number of rectangles, right? We needed n to go to infinity. And so either let delta x approach 0 and shrink the width of those rectangles. At the same time, that would make the number of rectangles go to infinity. If the number of rectangles go to infinity, right, then those little jagged edges, sawtooth edges, where the rectangles meet up with the curve, then will shrink and shrink and shrink until I'm left with the exact area underneath that irregular shaped curve. So there's our definition of the definite integral. Again, this represents the exact area between the function f and the x-axis over the interval a and b. And that is the limit of the Riemann sums. Okay, so the definition of an indefinite integral then, the definition of an indefinite integral is different. That's an antiderivative function. And so an antiderivative for f is, I've got space over here, an antiderivative for f is g of x if and only if the derivative of g equals f. What? An antiderivative for f is the function g if and only if the derivative of g is f, right? We could think about this in terms of a ladder, and gosh, I wish I could make a better drawing, but let's pretend we have a ladder, and on this ladder we're just going to have 2 rungs. I've never done this before, Scotty B, so that's crazy. So on one level of my ladder, right, I've got sine of x, and we'll call that g. And on the next rung down of my ladder, thinking down because I originally thought of this coming from the power rule, I've got the derivative of g prime. What's that? Kyle. So sine of x differentiates to cosine of x. Absolutely. All right, let's connect this now to our notation up there. An antiderivative for f is g, right? If and only if the derivative of g is f, and so this row must also be labeled what? This must be f of x, and stepping up one level must be an antiderivative for f of x. I'm sure glad that computational thinking used the microphone yesterday, because I just thought of this now. What a great visual representation. So now we know what we're talking about. We're going up and down the ladder. I can't wait for second semester when we raise the roof, we raise the bar, and we now go up and down the elevator. A little bit higher tech than just the ladder, but that's where we're headed. Okay. So now the mean value theorem made a connection between indefinite integrals and definite integrals that would allow us to develop the fundamental theorem of calculus. That is, exactly and algebraically evaluate a definite integral using an indefinite integral. So if g is continuous on a to b, and g is differentiable in between a and b, then we can find some c value. Call it x equals c on my interval, or with c in between a and b, such that the instantaneous rate of change, right, of g, that is the slope of the tangent line geometrically, is equal to the average rate of change over the entire interval a to b, that is the slope of the secant line. G of b minus g of a all over e minus a. And so once again, if we've got a continuous and differentiable function over an interval a to b, then the mean value theorem guarantees the existence of an x value, x equals c, in between a and b, such that the slope of the tangent is equal to the slope of the secant line connecting the endpoints. That allowed us to find the c value that, when looked up at the integrand function, right, evaluated in the integrand function, produced the perfect height of the rectangle. A perfect height of a rectangle such that when multiplied by the width of my subinterval resulted in the exact area no matter how curvy my integrand function was. And that's what the fundamental theorem of calculus allows us to do. So if f is an integrable function, that just means an antiderivative for it exists, and the antiderivative of f is g of x, then I can evaluate this definite integral, the definite integral of f on the interval a to b, simply by using that antiderivative function and doing what? Well, what is the definite integral of f over the interval a to b in terms of g, right? How can I evaluate that? Riley?
G of b.
Absolutely. We'll evaluate that antiderivative at the upper limit b, evaluate that antiderivative function at the lower limit a, and then subtract the two. And that's exactly what we did in number 2 of our Bellwork. We found an antiderivative for secant squared theta, that's tangent squared theta. We evaluated my upper limit, that's pi over 3. Evaluated my lower limit, that's pi over 6. Right? And then we subtracted the two. That is how the fundamental theorem of calculus works. All right, so we're going to hold off on these. I did decide to insert a practice day. So we're going to have a practice day with finding indefinite integrals and continue to practice with our antidifferentiation rules. And so we're going to go ahead and save these for a different time and make sure that we have plenty of time for our rules quiz. Again, we'll do the last 20 minutes of class will be the rules quiz. And so for us, we want to make sure that we're starting at 25, and then I'll make sure that you have the same amount of time as 2A did yesterday. So once again, we're aiming for 25. What we're going to do in just a minute is a partner pair jigsaw. And we're not going to go into our cooperative learning groups for that, but instead, each partner pair is going to receive a different color. There's Form A, Form B, and Form C. Algebraically, like number 2 from the Bellwork, you're going to evaluate a definite integral by hand. Then you're going to use your tech tip to check it, right? To check it numerically using the built-in functions of your graphing calculator. When you've completed all of the problems and check them with your tech tip, then you're going to raise your hand, and I'm going to come to you as a partner pair, and I'm going to give you guys both a stamp at the end. So once again, you're going to get a stamp at the end of the jigsaw. At the end of the jigsaw, then we're going to come back together and we're going to share our findings to formalize our properties of definite integrals. Then we'll have our closure, and we'll finish up by 25 so that everybody has 20 minutes to complete your rules quiz. Questions about what the rest of the day is going to look like? Okay, then I'm going to go ahead and pause the recording and get you your Raise your hand if you had 4 to 1 of negative 5. So who had from 4 to 1 of negative 5? And Peter, what did you get for that?
15.
15. So starting at the lower limit, 4. That's right here. And scanning towards my upper limit. So we always go from lower limit to upper limit. And in this case, that's that direction. So 1. I'd be left with this exact area. And yet, Peter gave us the correct value as a positive. So how can that be if my area beneath the x-axis counts as a negative contribution? Well, again, we're scanning, right? We're scanning from lower limit to upper limit such that my little delta x steps, right? My little delta x values are gained by doing b minus a. In this case, b is less than a, so that will result in little negative delta x values. And so little negative delta x values, when multiplied by rectangle heights that are gained by function values, in this case my function values f of c sub k are beneath the x-axis, therefore they're returning negative values, result in little rectangle areas that are the product width times height. That's negative times negative overall is positive. So when we sum up all those little positive rectangle areas, we get a positive 15. So again, when scanning right to left, now our area beneath the x-axis, our area below the x-axis counts as a positive contribution. Okay, let's go ahead and break up our pieces then. It looks to me like we've got the integral from 1 to 3 of x, and then the integral from 3 to 5, and then the integral from 1 to 5. And so let's go ahead and do the green part here. We'll go ahead and do the green part. 1 to 3 would be start at 1 and scan towards 3. And that would be this quantity here. And then we've got, the blue part from 3 scan till 5. And that's here, and that would be a pretty little polka dot region here. And then we've got the integral from 1 to 5, the whole shemam, starting at 1 and scanning until 5, and that will be the red portion. So how are the green part, the blue part, and the red part related? Well, part plus part equals whole. Who had 1 to 3? So who had 1 to 3? Katie? 4. And who had the blue part, 3 to 5? 3 to 5, Grace? 8. And who had the overall 1 to 5? 1 to 5, Michael?
12.
12. What's the relationship between blue part, green part, and red part? Well, part plus part equals whole. So we'll go ahead and do part plus part equals whole. What's my property? Well, I can break up an overall definite integral, right, at any x value in between, and then take the sum of the individual definite integrals to get the overall whole. Conversely, I could start with the whole and take away a part and be left with the other part. And so we could have started at my 1 to 5, take away the 3 to 5 contribution of 8, and I'd be left with 4. So part plus part equals whole. We could say the integral from a to c of f of x with respect to x plus the integral from c to b of f of x with respect to x is equal to the overall integral from a to b of f of x with respect to x with c in between a and b. So if c is in between a and b, in this case c would be 3, we can break up my overall definite integral from a to b into pieces. We go from just a to c, and then from c to b, and that would be equivalent to the entire interval from a to b. Okay, Who had negative 2 to 2 of x cubed? Negative 2 to 2 of x cubed? I think, Riley, didn't you have that?
Yeah.
So what did you get for that value?
0.
0? I thought definite integrals referred to the area, right, in between the function and the x-axis. How could we have a 0 area when I look at this graph starting at negative 2 and scanning towards positive 2? Clearly, I have two separate segments. Well, I do have two separate segments. It's just that area beneath the x-axis, and when scanning from left to right, counts as a negative contribution. And because my integrand function, in this case x cubed, is an odd function, that negative contribution is canceled out by the area of an equal and opposite positive contribution to the right of 0. These are exactly the same shapes and exactly the same contribution towards my overall definite integral. And so when integrating an odd function from negative a to positive a, the result will always be 0, right? That whatever portion above is going to be canceled out by whatever portion beneath. So our takeaway from this one is when integrating from opposite of a to a of an odd function, I'll call that O of d with respect to d for odd, or odd to d. The result is always 0. Won't find that in a textbook. I made that up too. What? It's in the dictionary. What about x squared? So negative 2 to 2, negative 2 to 2, who had that in our jigsaw? Negative 2 to 2? Peter?
I got 16.
Did you say 16 thirds? Who had negative 2 to 0 of x squared? Negative 2 to 0 of x squared. Grace? 2 and 2/3? I'm going to 2 and 2/3 bottom times the big plus the top. I'm going to put that as 8/3. Is that okay? And who had 0 to 2? 0 to 2, Tyler? 8/3? All right, so let's go ahead and get our picture. Negative 2 would be the red integral up until positive 2. That would be this whole schmam. The area of that region, scanning from left to right. Negative 2 to 0 would be negative 2 to 0 would stop here. So that would be our cute little polka dot region. And 0 to 2 would be here up until here. And that would be our green crosshatch shading region. I'm working on it. So what can we say? Well, look at that. Due to the symmetric nature of this even integrand function, that's an even integrand function, from negative a to 0, right, is exactly the same contribution as from 0 to a. And so to get the overall value from negative a to a, I could simply double either that left portion or the right portion. Oftentimes it's easier to evaluate this algebraically by hand, right? The right portion because it has a positive eval, and then 0 is easy to eval in an antiderivative function typically. So we can go ahead and say that that was equal to that plus that. And my takeaway is that when integrating an even function, right, from negative a to a, it's exactly double, right, from 0 to a. So let's go ahead and write that. Let's formalize that. So when integrating from negative a to a of an even function, we'll call that e of v with respect to v for even. The result is twice the value of 0 to a of e of v with respect to v. And that's supposed to be an A here. I don't know. It's not looking so good. Okay, ladies and gentlemen. That brings us to our closure then. So I want you to go ahead and fill in the blanks and be ready to share. The integral from a to b of f of x represents the area between f and the x-axis, so long as the area above the x-axis counts as blank. And and the area below the x-axis counts as blank. Okay, so in our typical scan with A less than B, scanning from left to right like we read a sentence, area above the x-axis counts as what contribution? That counts as what contribution? Colin? Positive, good, thank you. So area above is going to count as a positive contribution. Area below is going to count as what kind of contribution? Ishan?
Negative.
Negative, thank you. If my limits are flipped, right? If A is less than B, but B is my lower limit and A is my upper limit, then that's going to give exactly the opposite of the integral from A to B, right? Well, as we typically see. So, the integral from B to A of R of t, some function with respect to t, is going to be exactly the opposite as the integral from A to B of R of t. I can switch my limits around so long as I then take the opposite. That is -1 times the quantity. For integrating an even function from negative c to c, it's equal to exactly double the integral from 0 to c of my even function, call it e of v with respect to v. Versus an odd function integrating an odd function from negative c to c, right? Whatever contribution below the x-axis or above the x-axis will be canceled out by an equal and opposite contribution from the other side because of the graphical nature of an odd function. So this is always going to be what? 0. You guys are awesome. You guys are awesome. We're going to go ahead and scoot our desk to testing formation. We've got 2 minutes to spare. It's going to work out perfectly. I'm going to go ahead and pause and save the recording.